let's take a few minutes to look at what we can get, what kind of behavior we can get with ar2 processes. They're so much more interesting than ar1 processes, and what the autocorrelation function ends up being. And in the process, we'll actually simulate an ar2 process, which is a really handy skill to have. I'm on the ACF on ar2 tab. And in B4, I have the A2 parameter for the process I'm going to simulate. Right now it's set to 0. And in B5, I have the A1 parameter for the AR2 process I'm going to simulate. And in B6, I have the sigma value, the kind of size of the noise, the standard deviation of the noise I'm going to add. Then I have the time series table starting in A9 with the time values, some random uniform 0-1s in column B. And in column C, that's where we're going to simulate the autoregressive process. So for an AR2, you need to choose two values to begin with before you can start saying, well, the next value depends on the previous two values. Right now, I'm just going to put in 0 and 0. We can go back and think about that more later. And then now I'm on row 12 of the spreadsheet, which is time 2 of this data table. And we need to enter a formula that will use the A2 and A1 values in the previous two time points and some noise to generate a new value for this time series. So pause the video to think about that for a while and then come back. All right, welcome back. So we need to multiply the A2 parameter. So I'm clicking on B4, and then I'm going to lock that with $signs. Times the value of the time series from 2 steps ago, so that's C10, and I'm not going to lock that with $signs, plus the A1 parameter, which is in B5, lock it with $signs, times the yesterday's value for the time series, which is in C11, and then, so that does the autoregressive part, and then we'll need some noise. We have these uniform 0-1 values in column B, so I'm going to say norm_inv of, see I'm on row 12, so I'm just going to say B12, and then that would be a standard normal with standard deviation 1, but if we want a bigger or smaller noise value, we'd use sigma, so we're going to multiply by B6 and lock that one with $signs, and hit enter, and then paste it, and then fill it down. Right now our A2 parameter is set to 0 and our A1 parameter is 0.9. What does that mean about what this process is doing? Take a sec to think about that. It means it's basically an AR1 process because the 2 days ago parameter is 0, so it's basically just saying today is 90% of yesterday and ignore the day before that. And we can see on the graph of the time series, it's kind of herky-jerky up and down. We can try, but it's kind of hovering around 0, going up to just above +5, just below -10. We can generate new random sequences by pressing F9 on a PC or Control equals on a Mac. And sometimes the trace goes above 10. It went up to 15 at one point there, almost to 15 this time. But it's kind of hovering around 0. But once it goes above 0, it kind of tends to stay there for a while. Once it goes below 0, it kind of tends to stay there for a while. So that's an AR1 with parameter 0.9, even though we programmed this as AR2. Let's try sonifying that. So I'll set the selection, set the scale. Let's try how about a trumpet? So hopefully that's somewhat intelligible. Then I have all these other parameters to try, starting in I1 and I2. We can paste I1 and I2 into B4 and B5, and that'll give us an AR2 with a 2 coefficient of -0.8 and a 1 coefficient of 0.9. And that on the graph seems to jump up and down a lot, almost back and forth across the axis every other turn. Although maybe that's just kind of an optical illusion. If we look at the ACF, we see that the ACF at lag 1 is positive. It's about 0.49. We can get new new values for that. It's 0.48, 0.49. On the graph and also in columns G and H, we have bounds around 0, so horizontal lines at plus or minus 2 divided by square root of n. We say anything within those bounds is in some sense statistically non-significant. You have to be outside those bounds, either above or below, to be statistically significant. But that doesn't quite apply in all cases. Here the ACF is actually oscillating and dying down, so it gets as low as negative 0.8 at lag 3, but then it comes back up kind of through that non-significance band and up to a value of 0.56 at lag 6, and then back down to negative 0.48 at time lag 9. So it's kind of an oscillating but dying off sort of sine wave. We can try other stuff. Let's paste in from column J 0 and 1.05. Before I do that, take a sec to think about what that might give us. Ready? Here we go. Okay, we see strong like level for a while and then just diving toward negative infinity. It's like negative 4.5 million or something. If I regenerate the random numbers, sometimes it actually goes up toward positive infinity. That's basically saying we're growing at 5% per step for 200 steps. So that's plain old exponential growth with a little tiny bit of noise to it. The noise is what's determining whether the thing dives toward negative infinity or goes up toward positive infinity. And the ACF is pretty much all 1.0. It's not exactly mathematically 1.0, but it's pretty darn close within rounding. We said that if the A1 value is bigger than positive 1 or smaller than negative 1, then the time series is not stationary for an AR1, and that's what we're seeing here. We can paste in stuff from column L, where the A2 coefficient is 0 and the A1 coefficient is negative 0.5. And now that's really bouncing back and forth across the x-axis almost every other turn. Let's try something more fun. Let's choose, how about column Q, negative 0.99 for A2 and 1.98 for A1. And now, let's try sonifying that. It looks kind of like a sine wave, but let's... So it's oscillating, but it's growing in amplitude. We can try new random numbers and see if it always does that. Well, here it grows in amplitude at first and then kind of levels out. It's getting up to like 150, plus or minus 150. But something to note here is that the wavelength is not always exactly the same. It can be kind of randomly shorter or longer. Especially here in this random sample. It stayed quite low up to about 75, went just barely above the x-axis, and then came back down by time 100 again. And then the next wave was, the next positive wave part was about 40 long. If there was no noise, and actually we can turn off the noise by setting sigma to 0. And maybe giving it an initial value of 0 at time 0 and 1 at time 1, we see much more of a perfect sine wave, but kind of dying off as well. So this has links to differential equations and simple harmonic motion and all kinds of stuff. If you want to, you can go choose some of these other parameters from rows 1 and 2, columns I through T, and get a sense for how this behaves.